So hi everyone, the objective of our lessons are, at the end of the lesson, the students can determine the Greek mathematician and their contribution to modern mathematics and differentiate the ideas that they shared during the Greek era. So our first lesson is all about Greek number theory. So Greek number theory is of interest both intrinsically, because some of the natural questions that it raised have not been answered even in the present time. It was also the soil in which algebraic symbolism first sprouted. So this theory has two areas of interest. The first one is the Pythagorean topic of the arithmetic properties of figure-8 numbers. So these are the triangular numbers, square numbers, pentagonal numbers, and so on. So the next one, or the second one, is the theory of divisibility of integers. So it provides theoretical foundation for much of classical and modern number theory. So we have three classical Greek writers on number theory. The first one is Euclid. The second one is Nicomachus of Gerasa, and the third one is Diophantus. So our next topic or lesson is the Euclidean algorithm. So Euclidean algorithm refers to the procedure used to find the greatest common divisors of two numbers. So for you to understand this procedure or way of finding the greatest common denominator or divisor of two given numbers, here is our example. So let us find the greatest common measure or divisor of 26,173,996,849 and 180,569,389. So their common measure or common divisor or least common denominator does exist, and that is the integer 1. Pero ang hinahanap natin ito is their greatest common divisor. So based on Euclidean algorithm, the first step that we should do is to divide the larger number by the smaller number. So 26,173,996,849 divided by 180,569,389. So pwede na siya i-calculate or manual lang, and that will give you an answer 144 with a remainder of 172,004,833. So for our next step or step number 2, kunin nyo lang yung divisor natin sa first step and gawing dividend. And then yung remainder natin as new divisor. So that will give us an answer 1 with a remainder of 8,564,556. So sa ating step 3 naman, kunin lang natin yung divisor natin sa step 2 and gawing dividend. And then yung remainder natin sa step 2 bilang new divisor natin. So that will give us an answer 20 with a remainder of 713,713. So, ganun lang yung steps. Kung given ang two numbers, just divide the larger number by the smaller number, and for every step, kunin nyo lang yung divisor nyo and gawing dividend, and remainder nyo as your new divisor until mag-equal siya sa 0. So, our last divisor here is 7,013,713. So, it means ito na yung hinahanap natin na greatest common divisor or measure of the two given numbers. So the general procedure is to keep subtracting the smaller quantity from the larger until the remainder is equal to the smaller quantity or smaller than it. So our next lesson is the Arithmetica of Nicomachus. So relational properties were difficult for Greek philosopher, and Nicomachus expresses the concept of relatively prime numbers in a confused manner. Nicomachus explained the property in a rather wordy fashion in chapter 13 of Book 1, where he gives a method of identifying prime numbers that has become famous as the sieve of Eratosthenes. Nicomachus attributes this method to Eratosthenes from 276 to 174 BCE, best known for this work on prime numbers and for having estimated the size of the earth. So for us to determine the list of prime numbers using Nicomachus methods, the first step that we should do is to list all the odd numbers from 3 or starting from 3. So we all know that odd numbers are numbers that cannot be divided into two equal parts. So these are 3, 5, 7, 9, 11, 13, and so on. So ang step 2 natin is to remove all the multiples of 3. When we say multiple of 3, these are the numbers or result products of any odd numbers multiplied by 3. So, for example, 3 times 3, 3 times 5, 3 times 7, 3 times 9. So, we need to remove those numbers, those multiples of 3. And after removing the multiples of 3, proceed to the multiples of 5. Then, 7, 9, 11, 13. So, continuous lang yung pag-remove natin ng multiples of odd numbers until pure prime numbers na lang yung matira. Pero since odd numbers and prime numbers are infinite, we can only remove kung hanggang saan lang yung kaya natin. So this is how Nicomachus methods identify prime numbers, by removing all the numbers which are multiple of odd numbers. So that is. Our next lesson is factors versus parts perfect numbers. So Nicomache's point of view on this was different from us. So for example, 60. Usually, we think that the factors of this number is 2, 2, 3, and 5. But Nicomache's is different. That is why meron tayong tinatawag na superabundant, deficient, and perfect numbers, which is according to Nicomache's. So when we say superabundant numbers, these are numbers whose parts has a sum that is larger than the number itself. And it is compared to an animal having too many limbs by Nicomache's. So examples is 60. According to Nicomache's, it has a parts 30, 20, 15, 12, 10, 6, 5, 4, 3, 2, and 1. So when we're going to add these parts of 60, it will give us an answer 180. So 108 rather is larger than 60. So it is called superabundant numbers. The next one is deficient numbers. So when we say deficient numbers, these are numbers whose part has a sum that is smaller than the number itself. And compared it to an animal with missing limbs like the one-eyed Cyclops of the Odyssey. So example is the 14. So according to Nicomache's, 14 has a parts 7, 2, and 1. So if we were going to add this number, it will give us an answer 10. So 10 is lesser than 14, so that is why it is called deficient numbers. So the next one is the perfect numbers. So when we say perfect numbers, it is a number that is exactly equal. It is a number whose part is exactly equal to the sum of each part. So example is 6. So 6 has a parts 1, 2, and 3. So 1 plus 2 plus 3 is equals to 6. So Nicomache's gave a method of finding perfect numbers and stated by Euclid as Proposition 36 and Book of 9 of the Elements. If the sum of the numbers 1, 2, 4 is prime, then this sum multiplied by the last term will be perfect. So example, 1 plus 2 is equals to 3. So since 3 is a prime, multiply it by the last number which is 2. So the result will give us 6. It is a perfect number. Continuing, 1 plus 2 plus 4 is equals to 7. So 7 is a prime number. Then multiply 7 by 4, which is the last term. Then it will give us a result of 28, which is also a perfect number. So ganun lang yung pag-identify natin ng perfect numbers. So Nicomache's was able to generate the first 4 perfect numbers. He seems to hint at a conjecture, but draws back from stating it explicitly. It was found out that there is no regularity about the distribution of perfect numbers. Thus, Nicomache's was wise to refrain from making conjecture too explicitly. So our next lesson is figure-8 numbers. So beginning in chapter 6 of book 2, Nicomache's studies figure-8 numbers through polygonal numbers, through heptagonal numbers, and then polyhedral numbers. These numbers are connected with geometry, the number 1 being replaced by a geometric point. So Nicomache's speculated that the simplest way to denote any integer would be repeating a symbol for 1 an appropriate number of times. Thus, he said that 5 can be denoted as 5 A's or A. This train of thought, if followed consistently, would lead back to a notation even more primitive than the hieroglyphics notation for numbers, since it would use only the symbol for units and discard the symbols for higher powers of 10. So the Egyptians had gone beyond this principle in their hieratic notation, and the standard Greek notation was essentially a translation of the hieratic into the Greek alphabet. So these are the triangular numbers. On the left side, makikita niyo yung formula para makompute natin yung number of dots on each geometric figures or shapes. So, meron dyan yung triangular numbers, square numbers, and for the hexagonal numbers. So, observe that the figures are not associated with regular polygons. So, when we say regular polygons, these are the geometric shapes that has same sides and or equal sides and equal angles. So observe that the figures are not associated with regular polygons except in the case of triangles and square. The geometry alone makes it clear that square number is a sum of corresponding triangular number plus its predecessor, while pentagonal numbers is the sum of corresponding square numbers plus the preceding triangular numbers, while hexagonal numbers is the sum of corresponding pentagonal numbers plus the preceding triangular numbers, and so forth. So this mystical mathematics was transmitted to medieval Europe by Boethius. It is the same kind of analogical thinking found in Plato's Timaeus, where it is imagined that atoms of fire are tetrahedra, atoms of earth are cubes, and so forth. Since the Middle Age, this topic has been of less interest to mathematicians. The phrase of less interest rather than of no interest is used advisedly here because there are few theorems about figure numbers in modern number theory, and they have some connection with analysis as well. So next is Euclid's number theory. So here we will only focus on Book 8, which resumes the subject of proportion and extends it to square and cubes of integer, including the interesting theorem that the mean proportional of two square integers is an integer. For example, proposition 11, for example, 25 over 40 is equals to 40 over 64. And between any two cubes, there are two such mean proportionals. Proportion 12, for example, 27 over 45 over 75, which is also equals to 75 over 125. So when we say mean proportion, it refers to the square root of the product of two numbers. So makikita nyo naman dyan, 25 over 40. So it's very understandable naman.